Hello, dear students. This is Dr. Emmanuel here again with the weekly summary for week 2. So, in week 2, we did an introduction to limit state design. Before we talk about formulas or Eurocodes, let's start with the basic question. What does it mean to design a structure? Structural design is about making sure that structures are safe, usable, durable, and economical. We also have other aspects that the structure needs to meet, which includes sustainability, aesthetics, and design life. With the design life, meaning how long the structure would last. Historically, structures failed because engineers either underestimated loads or underestimated material strength. So limit state design was developed to manage uncertainty in a rational and scientific way. Now let us look at limit state design. Limit state design is a method that checks whether a structure reaches an unacceptable condition called a limit state. A limit state, therefore, is any condition beyond which the structure is unsafe or it is no longer performing properly. In simple terms, the effect of loads should be less than or equal to the resistance of the structure. So again, a limit state is any condition beyond which the structure is unsafe or it no longer performs properly. So we'll look at types of limit states now. There are two main categories of limit states that you must remember. One is the ultimate limit state, and the second is the serviceability limit state. The ultimate limit state is all about safety and total collapse. The ultimate limit state checks that the structure does not fail catastrophically due to bending, shear, compression, instability, or overturning. For example, a beam that has snapped has reached an ultimate limit state, or a column that buckles, or a slab that punches through a column. So in ultimate limit state, we are careful because if it is violated, lives are at risk. What about serviceability limit state, which is the second limit state? This is about the usability and the comfort of the structure, not about total collapse. So we carry out serviceability limit state, which we call SLS. SLS checks ensure that deflections are acceptable, cracks are controlled, and vibrations are not excessive. An example of a serviceability limit state, SLS, is when floors bounce when people walk, or cracking becomes visible in concrete, or there is excessive sagging of beams. If SLS is violated, the structure is safe but becomes unfit for use. So while ULS, the ultimate limit state, has to do with the total collapse of the structure, the SLS, the serviceability limit state, has to do with excessive structural behavior, which makes the structure to be unfit for use. So we will move next on to actions, effects, and resistance. An action is a load that is applied to the structure, such as permanent actions, variable actions, and accidental actions. An example of a permanent action is the self-weight of the structure. Another name for that is the dead load. An example of a variable action is what we call life loads. For example, the weight of human beings, or wind, or snow. An example of accidental actions are impacts and explosion. Good. So we now move on to effects of actions. Now, these are what loads do to the structure. and effects of actions are represented by the letter E. An example of what loads do to the structure are bending moments, shear forces, and axial forces, like you already know. Now let's look at resistance. Resistance is represented by the letter R, and this is the structure's ability to resist effects. The structure's ability to resist effects are based on the material strength, the geometry of the structure, and the detailing of the structure. So what is the core design requirement? The core design requirement is that the design effects of the actions should be less than the designed resistance, where ED is the design effects of the actions and RD is the design resistance, which means that the resistance of the structure should be greater than the effect of the actions, which keeps the structure safe. Now we are going to look at partial safety factors. One of the most important ideas in limit state design is that we do not assume that the loads or the strengths are exact and accurate. So we apply partial safety factors. How do we do this? We make sure that loads are increased so that we are conservative and material strengths are reduced. And why do we do this? Because in real life, loads vary. Materials are not perfectly uniform, and construction is not perfect. Does it mean that we are guessing? No. It only means that we are using a proven science method to be conservative. One important thing to note here is that for loads, we have factors of safety. But for strengths, material strengths, we use partial safety factors. So we increase the load by multiplying the load by the appropriate factor of safety. While for material strength, we reduce the material strength by dividing the material strength by a partial safety factor. I'll repeat that again. We increase the load by multiplying the load by the appropriate factor of safety, and we reduce the material strength by dividing the material strength by an appropriate partial safety factor. So if we have a 5 kilonewton dead load, the factor of safety for dead load is 1.35. So the design value of this dead load will be the 5 kilonewton force times 1.35, which gives 6.75 kilonewtons. So this is the value that we use in our design. On the other hand, if we have concrete with a compressive strength of 30 Newton per millimeter squared, the partial safety factor for concrete happens to be 1.5. So the design value of this concrete strength is the strength of the concrete divided by the partial safety factor, which gives us 20 Newton per millimeter squared. And this is the value that we use in carrying out our design calculations. So we have looked at partial safety factors and factors of safety. Partial safety factors are for material strength, while factor of safety are for loads. We increase the loads by multiplying by the factor of safety, and we reduce the material strength by dividing by the partial safety factor. Okay, next we're going to look at design working life. Now we must understand that structures are not designed to last forever. Typical design working lives for structures include temporary structures, about 10 years. We have conventional buildings that should last about 50 years. And we have bridges or bridge structures that should last about 100 years. The longer the design life, the lower the acceptable probability of failure and the more stringent the design requirements. Limit state design explicitly links safety to time. Next, we will look at probability of failure as a concept. Limit state design accepts that zero risk is impossible because engineering is all about acceptable risk. So the goal is to make failure extremely unlikely, socially acceptable, and economically reasonable. This is why we talk about target reliability, not absolute safety. So there are key takeaways from this video summary. The first is that limit state design checks unacceptable conditions. 2. There are two main limit states, ULS and SLS. 3. We compare design effect with design resistance. 4. Factor of safety and partial safety factors are used to handle uncertainty. This is the basis of the Eurocode design. If you understand limit state design, you understand why Eurocodes work, not just how to use them. In the next lectures, we'll be applying limit state design to real materials like concrete and steel, and you will see how these principles turn into actual calculations. Bye for now.